Good day! Today, I am going to discuss to you the introduction to integral calculus. It is interesting to note that the beginnings of integral calculus actually predate differential calculus, although the latter is presented first in most textbooks. However, in regards to formal, mature mathematical processes, the differential calculus developed first. The first steps towards integral calculus actually began in ancient Greece. In the 3rd century BC, Aristotle became interested in areas defined by certain curves. He used rectangles. This is not unlike some of the early methods trying to approximate the slope of a line that eventually led to differential calculus. He called this procedure the method of exhaustion. The famous mathematician Riemann would later generalize this procedure using the concepts of limits that were developed for differential calculus. The process, often referred to as a Riemann sum, is similar to Aristotle's rectangles, but the rectangles did not have a uniform thickness. Also, Riemann's method generalizes to higher dimensions, computing the volume. Since Riemann sums are not used today to calculate the area of a shape defined by a curve, the specific mathematics of them are not crucial to our discussion of integral calculus. Differential calculus was primarily concerned with the slope of a line tangent to a curve at a given point. This was helpful in a variety of problems, including computing the instantaneous velocity and acceleration. Integral calculus is concerned with the area between the curve and the x-axis. Calculating the area of a square, rectangle, and triangle, and other regular polygons, or even a circle, is a trivial task of plugging in known measurements into formulas. If you wish to know the area of a right triangle, you simply take 1/2 BH. If you want the area of a circle, it is pi times r squared. Even more complex shapes such as octagons have formulas you can easily use. A serious problem arises when one wishes to calculate the area of an irregular curve. Such shapes cannot easily be plugged into a convenient formula and the area produced. Take the following function for example. If the function were horizontal line, the area would simply be x times 1. But it is not a straight line. It is an irregular curve, making the answer significantly more difficult to compute. A good way to start approximating the area is to draw rectangles inside the area represented by the function. This simplifies the problem because finding the area of a rectangle is a trivial matter. This is, in fact, how Aristotle would have approached the problem. We might begin by doing this. As your rectangles get progressively narrower, your approximation will get better. Integral calculus helps us find that area and is, in essence, the opposite of differential calculus. Another term for integration is anti-differentiation. When you differentiate an equation, you get the slope. When you integrate, you get the area between equation and the x-axis. Put another way, the integrand or antiderivative of a function is another function such that the derivative of that function is equal to the original function. That is, if g of x is the antiderivative of f of x, then the derivative of g of x is equal to f of x. To illustrate the concept of the antiderivative, consider these simple examples. Since the derivative of x squared plus 4 is 2x, an antiderivative of 2x is x squared plus 4. Since the derivative of x squared plus 10 is also 2x, another antiderivative of 2x is x squared plus 10. Similarly, another antiderivative of 2x is x squared minus 20. Similarly, another antiderivative of 2x is x squared plus c, where c is any constant, positive, negative, or 0. And that is integral calculus. Simple and easy. Thank you for watching. Bye! 안녕! It's